Alrighty. Oi! Thank you. Now I need you to all be nice so I can take a picture of you all. Yay, it's my thing. I like selfies with you all. So I think we're going to try this end. But you all have to be really enthusiastic because I always compare my audiences against other audiences and then grade you. So I want big, happy waves while you're still here and enthusiastic before you're at the end and you're like, what color am I going to give her? It's green. It's always green because I will hunt you down. All right, are you ready for big waves? Okay, let me make sure this is wide. All right. Okay, I've got all of you. Maybe not you, but my head's blocking some of you over there, right? Big, cheesy smiles. Yay, awesome, thank you. That is your job's done. Now you just have to... Clifford, outrageous. All right, so welcome. Heed my warning in case you're sensitive to either of those things. But welcome to the forgotten AI of video games. I'm really excited to talk about this today. I'm really nervous as well, because I've never spoken about this topic before. I usually talk about other stuff, because this is me. This is my new bio type stuff. I'm the co-founder of November North Games. I am now a Unity developer, full-time, and I'm also these other things, like a game producer. I'm also the narrative designer, a script writer. I'm a financial director, you know, all those horrible things, a very bad 3D artist. I also do video editing, camera operating. I wash dishes. You know, I order the office supplies. This is what being an indie game developer is all about. You do all the jobs. But I really enjoy it. But you probably know me more for enterprise architecture. That was my previous life. I did a lot of things, especially modular monoliths. That's still my jam. I still enjoy that. But I have always been a gamer at heart. Even when I was doing my live streams, and this one's on Blazor and SignalR, I had virtual studios, and these are all done in Unity. And I would have all these bells and whistles with all these virtual studios. And I actually started, I went back to have a look, Unity in all the way back 8 years ago now. So I've been doing it for a very long time, on and off. But last year, I was laid off, like many hundreds of thousands of people. And I thought, well, what am I going to do now? So I changed to game development. And I've spent the past year figuring out how to make this NPC, non-player character, take this demonic hellhound for a walk around the block. So I have become an AI game developer type thing. So you do not know how long it took me to get this to work, okay? And now I've currently ripped that whole entire system out. But I'll tell you more about that. So we're going to talk about AI in video games in general. What does that mean? Well, let's take this nice example from Oblivion. Great NPCs there. Now, I did have some audio. I don't know if we'll hear any of it. It might come out. How dare you touch me? Pickpocket, that's what's being said. And as you can see, what controls these characters behind the scenes is a lot of AI, okay? And you'll have seen it in most of the games that you play. There's different types, so that was NPC AI. And then you have the AI that's in things like RimWorld. Who's played RimWorld? Not as many as I thought there would be. So RimWorld is a great game. It's really screwed up. Like, there's cannibalism, there's drug lords. It's really like, wow, okay? But everything that's controlling all the characters and the systems, even the world generation, the levels, is all some sort of AI. So if we come on here, what part does AI have in video games? Well, the general first part is as a player experience, like we saw with those NPCs, those characters talking to your player character. Excuse me. And it's something that the player can directly interact with, okay? Then we have AI as the content creator. That's what RimWorld had. We have those procedural world generation. If we think about Starfield, I'd rather not think about Starfield, biggest disappointment ever, but that was a really big procedurally generated world. What's the other one? There's that other space one. That's the one, thank you, No Man's Sky. Also, like 10 miles wide, about an inch deep, and that's what you get with a lot of AI-generated stuff, as we know, but, you know, besides the point. And then more recently, we've had it for character responses. They've been using LLMs integrated there, so you can ask a question to an NPC, and they'll give you some kind of answer back. Now, you'd need some kind of rule set behind that, so they have their character, but that's becoming more and more common, and I get asked a lot about that. And I'm also going to include AI for real-time rendering. So that's DLSS, Deep Learning Supersampling, which is an NVIDIA technology, where you can actually render your games out at a lower resolution and upsample it, and it smooths out things, it handles like a lot of the anti-aliasing, so you get a much better image without needing a much better machine. So we'll toss that in there as well. And then we have AI for modeling player behavior. Now this one's interesting. It's like the matchmaking on online games, cheat detection, nobody wants to cheat, and also like moderation. I think it was, let me see my notes, League of Legends. Yeah, they use AI extensively to identify and penalize toxic behavior, and that creates a much better environment for their players. So we've got all these different things that we can use AI for, analytics there, but we are not going to talk about those things. We are just going to talk about AI as part of the game. So, very specific little area of it, because that's what I've been working on for the past year. I won't be talking about any of these things. There's plenty of other excellent talks here that talk about that, so you can go to any number of those. But this one is not going to cover any of those. But I think it's really worth knowing the history of where the game AI that we're going to talk about actually comes from. I won't go too deep, but we'll have a little overview. So this classification, I actually stole this from Jodie in the front. Go to Jodie's talks. They are amazing. I've learnt so much about LLMs from Jodie, and I stole this from her. Well, actually, she took it from this Morris et al. Levels of AGI for I can't even say that, operationalizing progress on the path to AGI. Wow, that is a title of a paper. But what we have here is narrow AI classification. So that's AI that's really good at doing one particular thing. It's not very general, hence the narrow. So right down on the left, we have calculators, not really AI. And then we have this emerging AI, that's good old-fashioned AI. And you'll see here that it's saying it's better than an unskilled human. So this is how does it compare to a human. And then we go all the way up to like the superhuman AlphaFold protein folding knocks humans on their asses. But we are specifically going to be looking at this little bit here. Emerging narrow AI is how it was classified. Good old AI, but it also has lots of other names. Good old-fashioned AI, logic-based AI, classical AI, or symbolic AI. So we're going to call it symbolic AI because that's where we're going to see how it's come from that principle. So what is symbolic AI? But for this, we have to go back in time to the first AI summer. Did you know there were multiple AI summers? The first one was in 1948 to 1966. That seems like quite a long period. The second was in the 80s, and we are in the third. And that started around the 2010s with all the machine learning and obviously where we are now. So we are going back to that very first AI summer. And we're going to talk about GPS. No, not that one, but the general problem solver. And this was devised in 1957 by Alan Newell, J.C. Shaw, and Herbert A. Simon. Now, this was kind of built on a little bit of cognitive psychology and artificial intelligence, and they sort of built it on their research of human problem solving and heuristics. Now, heuristics is about getting to a certain point really quickly, taking a shortcut, assuming things. So we're going to think about that because it comes into play in quite a lot of the way we go through with our AI later. So they came up with this in 1957, and that was at the Rand Corporation and Carnegie Mellon, my God, these words, university. I was also talking very loudly at the speaker dinner last night because it was so loud, so I have kind of lost my voice. It will stay here for the rest of the talk, I hope. So let's go and have a closer look at what this is. Now, this is where the name symbolic comes from, because they use symbols, because they decided that human brains are really good at recognizing things, like a cloud, man, Game Boy, star, sunglasses, and trophy. These are all things that we can recognize and label and call symbols. These are kind of like your nouns. So it is based on the idea that human problem solving is a search process. And so we look at all the possible solutions, and it tried to represent that through states and operators and goals. And that language comes through in all the different types of AI we're going to look at later. And it used heuristic search as well. So that is, again, that sort of assumption that this is the shortest way to go. Rather than doing like a brute force, you can assume that's probably going to be the best way to go. Okay, so how does this work? Well, we can have a relationship, and then we can take these symbols and define how they are related and then come out with an answer. So in this case, we have a man and we have sunglasses, and if we put them both in, we can determine that they are cool, that this man is cool because he's wearing sunglasses. Okay, I am going to sneeze in a minute. It's all fine. Okay, so that's our relationship, and that's kind of how the symbols, in a very simplistic way, you can think of them. Now, if we go on to see what that actually looks like, we have these sort of calculations. So we have false, which is 0, and then we have true, not 0, and which is going to be multiplication, and or, which is addition. So let's go and see how that is put into practice. Is the kid wearing a cool old hat? So if we come here, we can have a, is the hat cool? Is the hat old? And is the kid wearing the hat? Okay, so if we times them all together on that top row, you can see that we've got true. And then you can go down, well, they're wearing a cool hat, but they're not wearing an old hat, so then it's false, okay? And we can keep going through all of this process, and we get our answers by simple multiplication, okay? So it seems quite straightforward. And is the kid wearing an old or a cool hat? So in here, we have the addition rather than the multiplication, and you can see anything not 0 is true, so we've got 2 at the top, and then we've got all the trues, and then finally we have 0 plus 0 times 1 is still 0, so it's false. So you can start to see how you could build up all of these relationships and define stuff. So it did demonstrate good puzzle solving and algebra and logic problem type stuff, and it did influence a lot of the AI we're going to talk about, but it did struggle with complex real-world problems, and because it exploded and got too complicated. Everything had to be formally represented, and it was eventually replaced by more specialized AI techniques, such as expert systems. So that's our next one. So these are predefined rules that simulate human expertise. They have these knowledge bases, and then they use these knowledge bases and an inference engine to make decisions, okay? So they sort of simulated a human expert. So we have that knowledge base, and then basically, if this, then that. And these were things, I think it was, what was the name? I can never remember it. Oh my God. There was one in the 70s that was basically medical diagnosis. So you had, if the person has this symptom and this symptom, we can determine that they have this ailment. So it went through that, and you can start to see it was if this, then that. And that was kind of what they went to. So they were very basic, but based on logic, and we could put all those in. And that was really early type systems. But they didn't have any common sense. They were very rigid. You needed to put all that knowledge base into it, so you had to keep updating all of that knowledge, and they weren't adaptable because you had to manually go and set up all of that, okay? So it was very intensive. But if you were doing things like insurance, fraud detection, medical diagnoses, very rule set, and with tight boundaries, they were good at helping to determine what an outcome could be. Okay. Now, you may be thinking, this isn't intelligent enough to be AI. It's some if-else statements, basically. But this is very much AI. It is completely AI. It's just not what you would say modern AI. It's not something you can have a conversation with, and it will write you a little poem about, you know, your pet donkey or whatever. But it is still very much AI. And it has a huge influence on a multi-billion-dollar industry that is video games, okay? So if we look at GPS, that's the general problem solver, it inspired AI planners and search algorithms like A-star, pathfinding, and HTN planning, all of which I'm going to explain momentarily. And expert systems led to the rule-based AI in games where, you know, the NPCs go, if this, then that logic, okay? And that's sort of behavior trees and GOAP. Again, we're going to go into it. And they both contributed to heuristic search techniques, which basically improves AI efficiency, giving you more FPS, which is always a good thing. No one wants a slideshow for their game. So by using heuristics, you can process things faster. Okay, so let's go into some core techniques. Now we've got the bit of history, we'll know what we're heading towards. So the first one is a finite state machine, okay? This is like your basic one coming in. Now I'm hoping we'll have this little bit of audio coming. Doesn't matter if we don't, I just wanted to get you in the mood to see if you're really my people. It's really quiet. No. Boo, hiss. Let me just see if I can whack the volume up. Let's go. All the volumes. Let's try it again. Okay. Fingers crossed. We're going to go again. I don't even know where my speaker is. Who gets goosebumps when you hear that? Yeah. I can't get it to work, Denny, so it's coming over the speaker from my computer. But who gets goosebumps? I always get goosebumps, even now. So that is like the Valve jingle, would we call it? Valve jingle. And of course, when you heard that, you knew you were going to be playing an excellent game, which is Half-Life, or Half-Life 2. No, not Half-Life 3. Well, maybe. They're teasing us. Who knows? Maybe. So Half-Life came out in 1998, and although that wasn't the first game to use AI, it was really defining in AI in games, okay? It used a finite state machine for all its NPCs, also known as monsters. Even the good guys, all the scientists, they were still called monsters, and everything was derived from that monster class. If you want to go and look at the source code for Half-Life, you can go in and get it. It's freely available out there, and you'll see all the states defined and what that looks like. So what is this finite state machine? It's a system where an AI character transitions between predefined states based on inputs or conditions. So in Half-Life, it would be your soldiers, they would have states such as patrolling, chasing, taking cover, or attacking. And let's say they saw you come into view as a player, they would go from patrolling, and they'd switch state to be attacking, okay? So it's very structured and it's very predictable because it's very defined. Now this came from a couple of different ideas and theories. The first being Mealy, which was a paper called A Method for Synthesizing Sequential Circuits. And you can see all of that. We won't go in there. If you want to learn more, there's a lot of documentation on it. So we had Mealy in 55 and Moore in 56. They're very similar, just one kind of looks at slightly different conditions to go in and define it. Okay, so they've been around for a very long time, but they did influence how the finite state machine was implemented in Half-Life. So, what does this look like in the games you play? Well, I've sort of told you what it could look like with NPCs. And in Pac-Man, we have them going through their chase, scatter, and frightened states. But what you probably experience all the time is your animations, okay? So your control, you are moving, you're standing still, you're jumping, you're running. That is a finite state machine controlling what animation is showing depending on the speed your character is moving, okay? So that's in most games. Okay, but they can get really complex really quickly. So we have this next stage on called a hierarchical FSM. Yes, I said that word. I always get stuck on hierarchical. So this can make it a little bit easier to manage. And they are very useful for modularizing your behavior. So you can have, if we go look at my diagram, we've got this NPC idle state. They're standing around, doing whatever, and they can transition to combat. And within combat, we have this other state machine transitioning through all these different states. And then we can transition through to wonder and duty, and we can have this very complex thing. So you can start to see how all of this can get really tricky really quickly. So I would say that FSM is good for quite tightly defined behaviors. You don't want to get too complex, all right? Now, I said I'd tell you some use cases for your enterprise apps. Well, we have the IBM's Watson for customer service and Dialogflow are hybrids of FSMs and machine learning and natural language processing. So, you can use them in business. Anything that's sort of automation, robotics uses a lot of FSM. Even your checkout systems will use that. It's really, you've probably used it in your own code without realizing it. Anytime you have like an enum and you're going through states, you're basically using some kind of state machine. All right, so our next sort of core principle is going to be behavior trees. Now, this is also known as a directed acyclic graph. And it's a collection of nodes, and it has a very fixed direction. We go down through the tree, and it flows top down through. It has a lot of different node types. We have selectors, sequencers, and then decorators, and they control the flow. So if we come and look at this diagram, we always have a root. Let's see if I can get my pointer to go. So we've got the root up here, and then we have a sequence. And as you might have guessed, a sequence needs to go through a sequence of leaves or nodes. And then we have a selector, so that will select one or the other. And you can have these nested and going down. So we have, these are composite nodes, so they manage and evaluate multiple nodes. And then the leaf node is always the one at the end, and it doesn't have any children. And that returns the result, okay, or does the thing. So how do we build those behaviors? We've got the AND gate, so think a little bit back to our AND OR in our GPS. So we evaluate usually from right to left. So we'll have the higher priority things that you want the NPC to do on the right, and then you'll go down through them. Now, with a sequence, if one child fails, then the whole thing fails. Whereas a selector, if one node fails, it will go on to the next one. If they all fail, then it will return fail, but it will do the first one that passes. You can set these to be random, so it doesn't have to go right to left to right. Yes. Left to right. So you can set them to be random. And then the decorators, these are like additional behaviors. We have the inverter, so whatever the result is, we invert it. We have something that will say, this is always going to succeed. So maybe you have an action that for some NPCs, you want them to evaluate it and either return true or false, but other NPCs, you always want them to do this behavior. You don't care whether they can or not. You just say, regardless, you're going to do it. So you put this succeeder one. We have a repeater, which will just repeat it. And you can put other logic in there that will say repeat until. And then you have the repeat until fail. So that's quite good if you have an NPC that, say, is going to eat an item. And every time they eat, they take some of the nutritional value of the item. And they keep doing that till there's nothing left. Okay, so that would be that kind of case. And then those leaves, if we have a look at those, a leaf has no children, it contains the action, and it also has the perform method. Now, we call this a tick. So I've got a little bit of pseudocode here, and because we play games continually, we run them on a tick. That's not always per frame. You can set a tick on a once per second, probably want it faster, but you can predefine what that tick is, and it will call that perform method every tick. So based on whatever it is, maybe has the NPC reached the destination, okay, we'll return success, or if we run out of time, we'll return failure, and we keep going through that. So they generally have these three states: success, failure, or running, and that's kind of what they look like. Now, just a little segue, we call where we store all the data in these AI systems blackboards. These are generally in-memory classes that just store data. So for all of your, let's say your NPC is hungry or tired, those values will be stored as floats on your blackboard, and you will have a process that will tick over those to either increase the values or decrease them. So you'll have them being ticked as well, so they're always changing and fluctuating, and it's these values on the blackboard that you evaluate for all of your AI systems. So if I talk about blackboards, that's what I am talking about. It's your in-memory data, and each NPC will have a blackboard associated with them, managing their feelings, their beliefs, they're often called, what they believe to be true. And you might have them for the world state as well. So like what doors are open, is it raining, is it day, is it night? So you'll have many, many blackboards throughout the entire system. So when you normally go into game development, you'll choose one of these: behavior tree or a finite state machine. Behavior trees are quite straightforward. They're modular, they're reusable. You even have behavior trees built into some of the larger game engines, so you don't even have to think about it. You can just start building out your behavior trees. They're also really easy if you have non-game devs. You can build a UI where they can start building them themselves, and they can do, oh, I want this behavior, and they can start doing all of that. they can be deeply nested. They can be hard to manage when you have all of these different branches. They are predictable, but they are very good for complex AI behaviors where the FSM, you can't really scale that. You saw that we had as soon as we started to go into the more complex stuff on that hierarchical FSM, you can see that was getting a bit of a mess, wasn't it? You wouldn't really want to have that much more logic in there because, yeah, that's not going to be fun to write a whole load of if-else statements on. So it just gets a little bit difficult. So we've got these two types, and if we went to FSM, behavior trees in your business app, maybe it will be like recommendations. Hierarchical system, you go down through the tree. Do they have this? Have they bought this before? You can recommend this. And again, robotics. So much of this stems from robotics. So those are our two basic AI types. Let's go into some more advanced decision-making techniques, because we can call this decision-making AI if we wish. But I am going to take this segue into NavMesh, navigation meshes. Not strictly AI, but it's so integral to the entire system. So let's go here onto this video. This was actually a debugging video I put up when I was helping on an AI navigation library. Now you can see there's a little capsule. He's right at the back there, and he is moving. Now the blue that you see there is a NavMesh, and you might just be able to see there's a green line, and that's him traveling to his destination. Now when he goes to his next destination, which is all the way over here somewhere, you'll note that he's going along, I'm saying here, is going to go along this pink line, okay, rather than the diagonal. Now what that is the pink line is saying this is where you should prefer to walk. If you've played Watch Dogs or GTA, you'll notice that all the pedestrians, they walk on the pavement. They use the crossings. That's because the NavMesh has NavMesh overrides on there that say, actually, this is where you should prefer to walk rather than just walking in the middle of the road. Likewise, any traffic will have theirs on the road. Okay, so it's really important for your navigation in there. Now, how did that come around? Well, there's several influences on our current modern NavMesh. So the first is a Voronoi diagram. If I've said that wrong, I apologize. I've heard it pronounced so many different ways, so I'm going to go with Voronoi. And I love this. If you ever watch a video on how these grow, you have these little dots or nuclei, and they start to grow outwards until they hit each other's boundaries. So this is a way of filling out spaces. And you'll notice that if we look here, like the two in the green there, they're equidistant from that border. And you'll start to see that they all grow out till they meet each other, and that's how they fill the space. I think they're really pretty. There's a couple of different types, but they're very useful in planning and partitioning spaces. Another one that was developed in the 80s for robotics was meadow mapping. And what we can see here is that the spaces were divided up into what we call convex polygons. Now, convex polygon is where all the internal angles are less than 180 degrees. And if you draw a line anywhere in that polygon, you will be within the polygon. So there's no like weird shapes where you would cross outside. So they have to be convex. So we divide them up there, and then that divides all of our spaces. And then the last one is the Quake's Area Awareness System. So that was developed at id Software. And again, we divide the map into convex polygons, and that's using binary space partitioning. And then we have these portals, aka doors, and we draw lines between those doors. So if you look at the start position of the agent to get to the target, it's really straight lines, isn't it? It's not very realistic. We don't all walk like that. We might meander a little bit through the space. So it's not great, but it was better than before. So all of these techniques got combined, well, Voronoi and the area awareness mainly got combined into our modern NavMesh systems. So we divide all of our area up into lots and lots of convex polygons, and then our NPCs can navigate across those. So this is from my game. There's several levels here, and you can see the blue is the NavMesh, and then so that's one level. We go up a level, and we've got more. And then if I take away some of the geometry, you can see how the NavMesh is up in the air, okay? NPCs generally aren't walking on your geometry. They are walking on NavMesh. So you could get rid of all game objects, just have this blue NavMesh, and NPCs wander around. So that's how it kind of builds up, and that's how your NPCs know where they can go. And if we zoom in right here, you should hopefully, it was really hard to get a screenshot of this. You can see we've got all of these polygons, and it divides everything up into polygons, and then that's what the AI agents navigate across. So how do they navigate across the NavMesh? Well, that's where the A-star algorithm comes in, and I am going to attempt to explain this. Okay, with this diagram. Are you ready? Okay, so let's define what these numbers are. We have F cost. Well, actually, let's start with G cost. This is our distance from the starting node. And then we have the H cost, H for heuristics. I told you it was going to come into play. And that's the distance to the end node. And then we have the sum of the two. So that's our actual cost. So let's come over to this diagram. Oh, I should tell you we have closed. That is nodes that we've already evaluated. Open the set of leaves. Notice the name change, leaves to be evaluated. And then accepted are the nodes that satisfy the goal. Okay, so let's go back here. We are at the start. Now, if you look here, if I go to the right, that's 10 from the start, okay, and then 10 here, you can see that's 10, and then 14 is the diagonal, because that's like, you know, the Pythagoras, 1.4 and 1 for a triangle, equilateral triangles, that's what we're looking at, then we are just timesing it by 10, so it's easier, 10 and 14 rather than 1 and 1.4, so that's where those numbers come from. And if let's go and look at this one. So if we go here, that is 10 from the start and 30 from the end. So that's 0, 10, 20, 30. Because it's heuristic, it's a straight line to the end. That's not the way we can go, but that's what we use. We're like, okay, this one is closest. So we will evaluate the ones that have the lower F cost first. So looking at that, we're going to look at 34 first, and we start evaluating around that. And then the next one we would evaluate would be this one with 38, then 40, and then 42. So we start going through all of these nodes and evaluating their cost by expanding them. Now, I want to come over to this one, because if I show you this one here, note it's green, so it's not been evaluated, and its numbers look weird. It's got 24 here, not 10. All the others around there were 10. That's because this isn't an evaluated node. How we get to this node is actually going here and then diagonally. Okay, so that's 10 plus 14. Okay, so it gets complicated, but you need to know that these values, I'll pop it down here, change depending on which node is being evaluated. So this is actually, these two have been evaluated after this one. So the route to that one is actually that way, left, and then down, hence 20. and this one here is left and then diagonal, okay? So the algorithm goes out. I'm going to show you a really good tutorial on this where I got this kind of diagram by a YouTuber called Sebastian Lake. He does the most amazing videos, and I strongly recommend you go and have a look at how he explains this. So we go diagonally here, and you can see we go across diagonally, and that is the cheapest one. We can see all of these costs, and 82 here is the cheapest route. So that's how we do that, through heuristics to try and help narrow down which is possibly the cheapest, okay? So we go through that, and that leads us nicely on to goal-oriented action planning. Yay, that was my life for the past year, aka GOAP. Yay. Oh my goodness. Even the mic didn't like that. Okay, so GOAP. This blew my mind when I first started doing it, and yeah, well, I'll show you how it goes. All right. Now this was in fear. All right. I'm really sorry for the low-res stuff. I got them off Steam. I stole them from Steam. So what's the stuff behind this? Well, Jeff Orkin, he was inspired by Stanford Research Institute problem solver, or STRIPS, and that really inspired him. Well, he was actually locked in a room for about 3 months. He wasn't an AI developer. He was more of a designer. And they said, you're going to do AI. And he was like, I am, okay. So he locked himself away in the room, didn't know what to do, and came up with this. And STRIPS has an initial state. It has a goal. And that's the expected outcome or effect. And it has a set of actions that have preconditions and postconditions, or conditions and effects. The name depends on which documentation you read. So let's have a look at an example of what that might be. So let's say you want to satisfy or reduce hunger. So you're on your blackboard, you've got this float scaling up, up and up and up of this NPC getting hungrier and hungrier and hungrier. They have a set of actions that can satisfy this goal, such as eat raw vegetables, yum, cook dinner, or buy, oh my goodness, ignore the typo, oh my God, buy takeaway. Okay, I'm glad that got you all to laugh. It was totally intentional. So we can buy those takeaways. Now we have some conditions here. Now it would go and look on the blackboard and say, do we have any money? No, they're broke. They say they can't buy a takeaway. So that means that they can't do that particular action. Now to cook dinner, they might need raw vegetables, so we can start stringing stuff together. Eat raw vegetables might not actually give them much of a reduction in their hunger. It might give them more of an expense, so you can set the cost. And cook dinner, well, maybe they need a cooking facility available. Okay, let's say they've got it. And if they do that, it's much more nutritious. They get a much more rounded meal. So depending on how you set up your system, your GOAP planner might choose eat raw vegetables because they're near death and we need food right now, or it might be like, we've got some time, let's go for the more nutritious meal, and it will cook dinner. Okay, so you start to get this behavior. Now, if we go to fear, this is all the goals that the enemy NPCs have. Guard, kill enemy, dodge, cover, and ambush. And these are all the actions that satisfy it. I found this really good video on YouTube that had a setup where they kind of show what happens. So we're going to watch this. Now this player has low HP, and then they are going to, let's go through here, all right? Doesn't matter about the sound, but. So he is hiding behind this box, and then he gets flanked, okay? And then they try and flush him out by throwing a grenade, and then they know he's over there being distracted by that one, and then another soldier comes around and flanks. Okay, so you can start to see how these goals are coming into play. So they're attacking from cover, they're hiding behind doorways, And the actual designers put nodes, like you can hide here, this is in cover, and they would go there. Now, a lot of, I'm just going to move that up there because we don't need the sound on that. Let me, there we go. So that was really interesting, and I missed that. What happened there was they actually threw down a cabinet to make cover. So we've got this really emergent gameplay. They're doing a whole load of stuff to make the cover, to flank them, to behave in a realistic, human-like way. And just to show you again, that's all they had to make that happen, okay? So it's really interesting how these get strung together. If you imagine them as domino pieces, so kill enemy, maybe it will go to node, blind fire from cover, and then melee attack. It could string all of those together to satisfy that goal of kill enemy, all right? So they start to string them all together and create an action plan. So if we just skip on past that, there we go. This is what this shares. Now, I did shuffle my my slides around, so I'm saying there's lots of games here, but we'll look at the games that also use this. The gameplay is really, really emergent. You don't know, as a designer or a developer, what the AI is going to choose, because you set all these variables and have at it, okay? So it's very unpredictable. This gives it realism because your AI makes decisions based on the world and the agent beliefs, and it makes them very adaptable because on the tick, it reevaluates all of this, and it can change plans based on changing conditions. So it's context aware, and it really is just awesome, okay? It does sound a little bit like behavior trees, but it's much more, I like to say open-close, because you can just keep adding action after action after action. You don't need to change anything. The system will just pick up all of those actions and do them, okay? So that's really good. So the games that use that were Far Cry 2, very good game, very enjoyable. All the Far Cries except Far Cry 6 were excellent. We don't talk about the travesty that's Far Cry 6. Stalker, Shadow of Mordor, Sims 3 and 4, and then my personal favorite game, Prey. So emergent, so excellent. If you've not played it, play it. It's amazing. So how does this work? We need to break it into two parts, and that is goal selection, and that's what we've got here. So that is based on the highest priority goal, and then based on that goal, it will go into action planning. So we go through all of this algorithm, and this is where A-star planning comes into it. And we'll look at all of the leaves that will satisfy that goal, and then we'll take the one with the cheapest cost. Okay, what is going to be the cheapest for our AI to do? And then we take that node, and because if you look up here, each node has the parent, the cost, and the action associated with it, we can go back up through all of those nodes and see what the plan is. And that might have 20 actions in it to get to that end goal. All right, so it's really flexible. And it all stems from A-style pathfinding. So this is how the algorithm looks. There's a lot of recursion in it. So it kind of blows your brains a little bit when you try and do it. But this is how it is you could use it in your business apps. I think the one where I see it most is anything human organizing, smart scheduling systems. Because you could have, who's on holiday, who works these days? You can put all of these conditions into the pot and come up with a schedule for like 1,000 employees. And you don't have to do it. You can put it all in there, and it's done. There's a business app idea for you folks. And there's lots of different things like tickets and prioritization. It does have cons. It's really unpredictable and difficult to design players' interactions, and it can be so expensive, okay? My goodness, if it's not optimized, your FPS, your frames per second, will nosedive. Now, that's what happened, the difficult to design the player's interaction for War of Cybertron from High Moon Studios, okay? They used GOAP in that. So when they came on to do Fall of Cybertron, they're like, we're not doing GOAP, no more. So they chose Hierarchical Task Networks, HTN. 3 weeks ago, I ripped out all the GOAP out of my game, and I implemented HTN because I was done with GOAP. It's too many knobs to turn. So I have implemented HTN now. So I can see how they got to that. And a lot of games now have moved to HTN over GOAP. So what does this do? It's very structured. It's very efficient because you can do partial plans. And it really, you can see the design. It's very natural. It's got a lot of domain knowledge, so you can give it very specific strategies to do it. It still has the flexibility of goal-oriented. You can really do a whole load of things in it. But it's really like the best of both worlds, I think, okay? So each high-level task is broken down into smaller tasks, and we run it. You know what? Let's have a look at the diagram. That's going to help, isn't it? Diagrams are always better. This is actually from a really good, I've got a resource page for you all, so don't worry. I suggest, if you're interested, go and read lots of things on this website. But we have Bee Tree Thumper. So this is from that paper. So this is a troll who's a tree thumper. And you can see the orange are all the conditions. Can they do this? And this goes from left to right. So the highest priority here is to attack. And then it will go through all of these hierarchies and then left to right. So it's a bit like a behavior tree, but not. And it will start to come up with a plan. And the plan down here, navigate to enemy, find trunk, navigate to trunk, because they don't have one, uproot trunk, do trunk slam. And it gets, you can have so much control while still having some of that emergent behavior. It can get very deep. And if we go here, where I say recursion, if it's going down more than 100 levels, you want to do it in an iterative fashion. So it supports both. But again, it's a lot of if, else, you know, if this is true, do that. If not, loop and do the next one. And you can see we've got our domain. That's all of the actions that an NPC can have. And then we have the world state, and then we have their plan coming out of it. So we'll look at the primitive task, which is one of those individual, like, do a tree thump, okay? If not, it's a composite hierarchy one. So we'll come down and we'll run the method. Each of those is called a method. Do the preconditions get met? If so, we're going to run that because we don't need to evaluate the rest of it. We're not looking for the cheapest. That's a GOAP thing. So we can run the first one that is positive. So that makes it much more efficient than GOAP, all right? I think they were saying on Fall of Cybertron, they had like something like 30% more efficiency. Don't quote me on that, but I know that it was massively more efficient. Killzone 2 and 3 both use that. Horizon Zero Dawn is one of the most famous for using HTN. They use it for all of their robot dinosaur herds. So that how they plan out all of their attacks are all handled by HTN. So they use it a lot for that sort of squad behavior. Dying Light also use it, and so they say Dark Souls uses it. I've never played Dark Souls, that's not my kind of game, but apparently it's very popular, but you know. So the type of thing that you could use this in is project management tools, stuff where you've got nice structure, big tasks, and then subtasks within it, okay? Now, GOAP versus HTN, the difference is GOAP is backward planning. Remember, we go all the way down until the very last thing that succeeds, and then we go all the way back up. Whereas HTN is forward planning. It goes, can I do this? No. Can I do this? Yes. That's it. That's as far as it goes, okay? And there's a very difference in the structure. It's hierarchical, and GOAP is very flat. Remember I said you can just shove all those goals in. That's less so with HTN. You need to give it much more of a structure. GOAP is just like, yeah, whatever, have at it. So that leads us on to high-level systems. These, I would say, are more complementary AI systems, and they work in combination with other AI systems. Now, the first one we're going to look at is called director AI. And this is to manage pacing and flow. It's the director, like a movie director. It's directing the game. And so it orchestrates and influences all the other AIs. So it doesn't actually do anything in particular with the agents, but it maybe affects their blackboards, that kind of thing. Okay. Alien Isolation used it a lot to maintain suspense. So when the xenomorph didn't have you on their scent, they were just plodding around, and it would slow the animations and transitions down of the xenomorph as it was going around. If the xenomorph had seen you or was slightly alert, you'd made a sound, the director AI would speed up the animations and the transitions between animations to make it move a lot faster, to build suspense and scare the shit out of you, basically, okay? So you'd be like quaking inside your locker going, don't breathe, hold your breath, hold your breath. And that's what it was doing. It was trying to get you to do that more. Far Cry 5 has it to manage NPCs, whether they're active near you or not, okay? And that was mainly for performance. And then Left 4 Dead did it to make sure you played by their rules. If we look at this breakdown from Tommy Thompson at AI in Games, basically we have the director AI going through an FSM, building up tension, throwing more zombies at you, peak where your stress is max and you're like, oh my goodness, I'm gonna die, we're all gonna die. And then after you do that, giving you like 30 seconds reprieve. Now this actually was meaner to you if you didn't stay in your squad. If you were like, I'm not staying with those three, and you went off on your own, the game didn't like that. The director AI is like, you're not playing by my rules, we're gonna send more and more zombies at you and kill you. So it's very much about getting you to stay where it wants you and do things like that. Now, the last one is utility AI. And this is just a way to make sure, is this the best option? It, again, works with other AIs. Maybe your GOAP system comes back with 2 possible plans, and this one will be like, well, we could do the cheaper one, but actually I think this more expensive one is going to be better. And that's something that the NPCs in Sims 4 did and utilized quite well, and that stops them getting stuck in a loop. So if they'd already done that, be like, actually, you've already done this, let's go and do that. So it can give you a more dynamic feel to it. Other games that used that was Dragon Age Inquisition. Again, Alien Isolation used that as well. And then there's hybrid systems. All of these AIs can be munged together, okay? I've seen hybrid GOAP systems where you have the action and it's got a finite state machine within it. You can have HTN with behavior trees inside it. You can basically anything can have anything else inside it, and then it just becomes mind-blowing, okay? So I tell you, my personal experiences with this over the past year is I have never written such performant code in my life. Web developers were lazy. Throw more servers at it. Throw more CPUs at it. You want to try and optimize on a game that's ticking every frame, oh my goodness, you become really anal about every little thing, okay? You approach things from different ways. I've been doing much more data-driven, trying to take my object-oriented brain out of it and look at data and how to process that, because you can do that massively in parallel, which makes a game more performant. I have regular brain melts. That's my personal experience. Rage quitting as Unity crashes on me yet again. Why I think you should give it a go is I want your brains to melt also. It will make you a better problem solver. You will think about things in different ways. You will think about systems. You can take any of these AI systems I've got, any of these algorithms, apply it. You will be a better debugger and able to diagnose problems more, because Unity or any engine that you do, they don't help you. It's really difficult. You're like, why is my NPC doing this? What is going on? Why is everything broken? And it will make you really good at thinking for yourself and problem solving. And plus, it's really fun. I've spoken about a lot of things, and there's so many papers to look at. So if you want to take a picture of this, you can see there's a link there. I've put a whole load of resources in there, links to videos, papers, all sorts of things. There's so much there. If you're interested, you can do that, or you can reach out to me at layla.dev. If you want to follow my progress of my video game, it's codenamed Horror Town, and I've started posting devlogs. And you can go and there, it's a first-person stealth game. So you can come and follow all of my trials and tribulations there. And with that, I want to say thank you for coming and listening to me talk about something I'm really, really passionate about, still learning loads about. And I know I haven't got time for questions, and you probably really want your lunch, but I'll be here. You can come up and talk to me if you wish to do that. So thank you so much.